Hello everyone. In this video, I want to have a conversation regarding a tankless water heater from the point of view of a homeowner. Well, me. I've owned a tankless water heater now for about a year and a half. I've already made one video on maintaining the tankless water heater. I'd like to have another conversation regarding owning a tankless water heater. But before I get onto that, many of you that have been following me, you'll notice that behind me used to be two bookcases filled with physics books and chemistry and math and metallurgy and various other courses that I taught at the college. Now, well, I took everything out, and you saw it in past videos, and I removed the two bookcases, and I painted the walls. So I have here, well, an empty canvas. You can have a look. It's all painted. In this space, it's my intention to put in a bunk bed for my grandchildren. But that's for another day. Today I want to talk about tankless water heaters from the point of view of the homeowner. Now, there is going to be some physics and there's going to be a little bit of mathematics in this video. It's important to know something about physics, something about nature, and I'm going to prove that to you here in this video. Now, when I bought the water heater, I was given this manual. Now, you've seen this manual in the prior video. It's my hope and my wish, actually, that I wish I had this before I bought the tankless water heater, because there's a great deal of information here for this video. And there's lots that I can talk about now that I've actually had one for a year and a half. But for this video, I want to talk about this one specific graph. As soon as I find it. This one right here. This bottom graph. So, well, let's get started. Before I went ahead and bought the tankless water heater, I did do some homework. I researched YouTube videos, as many as I can find. I tried to find some literature somewhere, and I can find some information from Rinnai and various other manufacturers, and they also made videos regarding their product. And what I did see on YouTube was a lot of contractors installing tankless water heaters and explaining how great they are and how to maintain a tankless water heater, putting one on the inside of the house, putting one on the outside of the house. All of this from the point of view of a contractor installing or from manufacturers trying to sell you their product. But what I didn't see and what I couldn't find is a point of view from an actual homeowner who owns a tankless water heater and trying to learn the ins and outs of actually owning one. Well, it's been a year and a half, and I do have some information to share with you regarding actual ownership of a tankless water heater. And that's what this video is about. Let's compare a tankless water heater versus a hot water tank. Here I have two homes. Here's the basements of the both homes. This particular home has a tankless water heater, and this one has a hot water tank. Now, the tankless water heater only comes on when you turn on a tap. Only when water is running. All the other times it is off. Since it's off most of the time and it's only running when you're running water, you're going to save on, assuming both are running on natural gas instead of electricity, so you're going to save on natural gas. The natural gas bill. There will be a slight savings here because you're only using the natural gas, only time when you're actually using water. Now let's look over here. This hot water tank is on all the time. It's always hot. There is a flame here. And whenever the temperature of this drops below a certain level, the pilot will light up the flame here and heat up this water tank. So water here is always hot. As a result of this going off and on, continually keeping that water temperature hot, it will cost a few dollars. Costs more to operate. Well, let's have a look at a little closer on this one. Now, water or heat I should say, heat travels one way, as I said earlier or later on in this video. Heat travels one way from hot to cold. So as this water tank here is hot, and these pipes, here are the pipes going from the water tank to a kitchen and to a bathroom on the first floor and going to a bathroom on the second floor. There is water in these pipes, completely filled with water. And the temperature, let's assume the temperature of the water heater here is in degrees Fahrenheit, 110 degrees Fahrenheit, constantly. Since heat travels one way, hot to cold, this is continually losing heat. So it's going to lose heat to the ambient atmosphere. As it loses heat, the gas burner is going to come back on and bring the temperature back up to 110 degrees Fahrenheit. So this is continually going off on. And that, of course, costs money in natural gas. Moreover, because heat travels only one way, the hot water here, the heat from the hot water here is also heating up all of the water in these pipes. So the temperature of the water in the pipes is not exactly 110, but it's also hot. So let's say it's 100. Say the temperature of the water in those pipes is 100 because it too is losing heat into the ambient room temperature. So if the ambient temperature in the wintertime, let's say, is 18 degrees Celsius, or what would that be in Fahrenheit? Let's have a look here. 18 times 1.8 equals plus 32, 64 degrees Fahrenheit. Yep, there you go. Then the room temperature is 64 Fahrenheit, and the water temperature is 100. The heat from the water pipes here is going to lose heat into the room. And the same thing here. But the water temperature in this pipe is going to stay basically at 100 degrees Fahrenheit. Because the temperature of the water here is continually being heated, that heat, I should say, is rising, heating up all of the water in these pipes. Hence, the moment you turn on a tap here in the kitchen or turn on a tap in the bathroom or here, you will get instant hot water. So the benefit of this is instant hot water. There is a price to be paid. So when you're sleeping at night and you're not using any of the water, this is still running off and on, off, and it's still going to cost you some amount of money in order to run this in terms of cost of gas, using your gas usage. On the other hand, if we look here at the tankless, in the case of the tankless water heater, since it only turns on when the water is running, this is off. As a result of always being off, you're going to save something here in a natural gas bill. But the temperature of the water in these pipes is also cold. It's the same temperature as the room temperature, say 64 degrees Fahrenheit. And when you turn a water tap on here, you're going to get 64. And you're going to have to wait for hot water. So there's a trade-off. Here you're constantly heating up the water and using natural gas. And here you're only using natural gas when you turn the water tank on, or the pipes on. Here is the manual that came with the tankless water heater from Rinnai. I got this after I bought the unit and it had it installed, and this came with it. Tankless water heater for the residential. Now let's have a look inside. There's plenty I can talk about. I'm sorry I didn't have this to look at before buying the tank. There's plenty of information here that I could be happy to discuss and look at, but right now for this video I want to look at just one graph. I'll just skip all this other stuff and go straight to what I'm most interested in right now, and that is this graph right here, this chart. For this video I'm interested in this chart. Down at the bottom for this chart we have temperature. It says temperature rise, and I'll talk about that shortly. And over here on the left we have water flow. Water flow, or volume flow rate. I'm just going to zoom in a bit. Water flow is in gallons per minute. Now they call it water flow, but it is actually water. It says volume flow rate. They call it water flow in gallons per minute, but it's actually volume flow rate, or the same thing as volume flow rate. If you want to talk fluid mechanics and in the world of physics, it's volume flow rate, and volume flow rate has the symbol Q dot. The units for the volume flow rate is in gallons per minute, or GPM. So let's have a look at the volume flow rate of the water through the kitchen sink. Here I am in my kitchen. Here's my faucet, on, off, and I have a container, and this is in liters on this side, and here's the 2-liter mark. There's different ways to do this, but I'm going to try it this route. And I don't have a digital clock, but I do have this clock here with a second hand. And when that second hand reaches the 12, I'm going to turn on the water and see how long it takes to fill up the 2 liters. I'll keep the two together. There's 15 seconds. 20 seconds, 22, 23, 24 seconds in order to get the 2-liter mark. I'm going to repeat what I did. I'm going to wait for the clock to go to 12, and we start. Here's the 2-liter mark. Clock is at 10 seconds, 11, 12, 15, 16, 17, 20, 23, 24, about 24 seconds yet again. Then there's the 2-liter mark. And can watch out for that parallax. There we go. It's looking good. So again, 24 seconds for 2 liters. We need to calculate the volume flow rate. So I did a demonstration of this in my kitchen sink, where I had a volume of water filling up a 2-liter container. But now let's have a look at the mathematics involved. Volume flow rate in fluid mechanics. Volume flow rate is represented by the letter Q and a little dot on top to indicate it's a rate. So it's something per second. So Q dot, volume flow rate, is equal to the velocity of the fluid exiting the pipe times the cross-sectional area of the fluid, or of the pipe, I should say. So if we do a little sketch of my kitchen sink, here is my faucet, and the faucet is a tube. It's a circular tube. So water flows in here, and for this to work for our purposes, the tube has to be filled with water, which it is. It's completely filled. So water enters here, and it exits here. And the volume flow rate here at the exit, we're interested in, is the velocity of the water. The velocity of the water here at the exit as it flows out, times the cross-sectional area. And since this is a pipe, the cross-section of a pipe is generally a circle, and the area of a circle is pi r squared. And this is the area we're interested in, this cross-sectional area right there. That would be here. If we just look at the units, without doing this calculation, if we just look at the units, the volume flow rate, looking at the units only, velocity in the metric system, velocity is in meters per second, and area, if I were to calculate the area here in the metric system, will come to meters squared. Therefore, the units for volume flow rate is equal to meters times meters squared divided by seconds, and this comes to cubic meters per second. Now this would be the volume flow rate in the metric system. The chart, which we are looking at, it happens to have the volume flow rate in terms of gallons per minute. Gallons per minute. I'm going to take a wild guess and say that this is actually US gallons per minute, not the Canadian gallon per minute. So the volume flow rate is in US gallons per minute. Having said all of this, let's do some calculations of the volume flow rate of my kitchen faucet. We know we're filling up a container of 2 liters. And the time it took to fill 2 liters was, I believe it was 24 seconds, maybe 25. Well, I'll go with 24. And I did it twice, and each time it come to about 24 seconds, give or take a second. So let's say it took 24 seconds in order to fill up 2 liters. Therefore, the volume flow rate in these terms right here, it was, and we want time on the bottom. So it took 24 seconds, 2 liters. Took 2 liters to fill. It took 24 seconds in order to fill up 2 liters. So we have liters per second as far as the units goes. And often when I taught physics, I would teach my students how to manipulate the units, work with units. And that's what I'm going to do here. We have to convert this to gallons per minute. So 24 seconds to fill up 2 liters. I'm going to multiply that by some conversion factor. And if we look at liters, the conversion factor for the US gallon, 1 US gallon is equal to 3.8 liters. Knowing what this conversion factor is here, let's put these values here in our equation. And we want to cancel out the liters, so I'm going to put the liters in the denominator, 3.8 liters, and put the US gallons on the top. That way the liters cancel out. And I need it in minutes, and I have seconds, and we all know that 60 seconds is equal to 1 minute. So multiply this, and looking at seconds is in the denominator. I want seconds in the numerator. So it's 60 seconds in the numerator to 1 minute. Canceling out the units, seconds and seconds, what I have left is US gallons per minute. So the volume flow rate for my kitchen sink, we do this calculation. It's 2 divided by 4, 24 I should say, 2 divided by the 24 is equal to, divided by 3.8, divided by 3.8, and it's equal to, and I'm going to multiply that times 60, equals. So my volume flow rate is about 1.32, let's just round that a little bit, 1.32, and the units is the US gallon per minute. Or to simply simplify this, the volume flow rate for my kitchen sink is approximately equal to 1.32 gallons per minute. Or 1.32 gallons per minute. I have a little setup here. I'm going to check the temperature of the water as it leaves the spout. I have a clock next to it and a temperature gauge, well, thermometer. Need to know what the temperature outside is. Hey Google, what is the temperature outside?
The temperature in Hamilton right now is -2 degrees.
So we'll keep that in mind. Temperature outside is -2 degrees. When the second hand here hits the 12, I'm going to turn on the water. I'm going to go to hot water, set it over to hot. And I got this set up such that the tip of this thermometer is in the water stream. I'm going to try and keep it there. There it is. And the temperature of the water starting at 64 degrees. I got it in Fahrenheit because it's a finer scale than Celsius. So it's gone up to 65, 66, 67, up to 68, 67. Now it seems to be going down, and it's going down again. So it started going up and now it's going down. 61, 60, and the water itself, I put my finger here, yep, that's cold. 58. And make sure this is in the water stream. Yeah, it's in there. Now it's going back up again. 63, 64, 68. If we look at the time, a minute has gone by. 81. It's climbing. 91. 95. And it's just about 2 minutes has gone by right now. And the temperature has reached 97. So it took 2 minutes in order for this water to get to a warm temperature. 100. I put my finger here. And that's warm. A body temperature is 98.6 Fahrenheit, so this will feel warm. It's at 100. Now it's going to stay at 100, 101 indefinitely, as long as I have gas going to the house and water running. The thing about having a tankless water heater is, well, you can keep the hot water running for a long time. It will continue to give me this temperature, 100, 101, and it will stay here constantly. You can see. I think it's almost 4 minutes now. No, 3.5 minutes. (102), 103, and I have this set at full throttle. It's open maximum. I find that if you only say halfway through, it won't reach this temperature. Halfway open, I should say. So we need to keep it at maximum temperature opened up as all the water goes through, and it'll come to temperature. And I'll just wait another 40 seconds. Make it a full 5 minutes. Get the clock here. Yeah, another 30, 40 seconds, and it'll be a whole 5 minutes. And the temperature is 103. If I put my finger here, yeah, that's warm. I'm always got it running a full 5 minutes. It took 2 minutes in order for it to get to temperature. And here we are, last couple of seconds. Let's take a look at the water temperature a little closer. Over here I have two columns. One is time in seconds. 0 seconds, that's when I first open the tap. 1 second, 2 seconds, 3 seconds. And then it goes on, eventually gets into minutes, but I didn't do all the time here. So at time equals 0, the temperature of the water coming out of the spout was 64 degrees Fahrenheit. And I chose the degrees Fahrenheit because it's easier to see the change in temperatures rather than degrees Celsius. So it started at 64 degrees Fahrenheit, and then it started to rise, 65, 66, 67, 68, and it sort of plateaued a little bit, and then it came back down, 67, 66, 65, 64, and it started to drop down to 60, 58, and then it started to rise again after the 58, 61, 62, 63, and it continued to climb up to, at 2 minutes, it was 96 degrees in Fahrenheit. I'll put down here degrees Fahrenheit. This is good, a column, but it's easier to see something when it's graphed. So I made a graph. On the y-axis is temperature in degrees Fahrenheit. And I started here at 50 degrees Fahrenheit. This little zigzag means I'm truncating the graph. Instead of starting to get 0, I'm going straight to 50. And time along the x-axis. And I didn't do the actual seconds, I just wrote down what the 2-minute mark was right here. And if we look at the graph, when I first opened the tap, or turned on the faucet, the temperature was 64 degrees Fahrenheit, and it started to rise. It went up to 68, and then it started to dip. And then you can see here it went down, 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 down to 58 degrees Fahrenheit. And then it started to rise again. Started to rise till eventually it reached the maximum of about 100 degrees Fahrenheit. It's also good to note that the outside air temperature was minus 2 degrees Celsius or 28 degrees Fahrenheit. Let's analyze this graph a little further. I drew here a quick sketch of a house, typical house. And here is the house itself. Here's ground level. So this is above ground, and of course our houses here have a basement. So here is the basement. I'll write down here basement. In the basement, against this wall, is where I have my tankless water heater off to one side of the wall. And it exhausts outside. It comes up here and exhausts outside. Water coming into the tankless water heater is underground. So here will be a water pipe of water coming into the tankless water heater. We'll come back to this in a moment. As it sits here, there is no heat going on. There is no gas. Nothing is happening. It's just sitting, resting. Nobody is using any water, so there's no water flow. So if we take that scenario, and there's no movement of water, there is water in the pipes, and these lines here represent the pipes in the house. So here's a main pipe coming from the water tank, and it comes across along the basement and up here to the kitchen, to the water faucet that you saw me use. And there's also a splice, and we'll put this one here into a bathroom on the main floor, call it the shower, any bathroom. So there's a splice, and there's a water line going to that shower, main floor. And there's another splice here in the pipe. So water travels up and goes to a bathroom in the upper floor, a shower, and a sink. So the bathroom in the second level. Typical temperature, and we're talking the winter time now, so the outside temperature in the winter, as you saw, is minus 2 degrees Celsius. That translated to 28 degrees Fahrenheit. Minus 2 degrees Celsius, well, that is below the freezing temperature of water. Therefore, the water actually coming into the water tank right here cannot be minus 2 degrees Celsius. It has to be above zero, otherwise it wouldn't flow, it'd be ice. Typical water coming into the house here and here, I'm going to shoot for about 4 degrees Celsius. Could be more, could be less. I chose 4 for a specific reason. Any of you that are studying fluid mechanics, you will know why I chose 4 with water, but for now I'm just going to use say. So let's say the water coming in is at about 4 degrees Celsius. So let's look here. So there's no movement of water. Room temperature in the basement and here and there is about 18 degrees Celsius. Again, we're in the winter time, so outside temperature is minus 2. Inside temperature is about 18, and that translates to about 64 degrees Fahrenheit. So the room temperature is 64 degrees Fahrenheit, all these room temperatures 64 degrees Fahrenheit, and heat travels one way. Heat travels one way. One way. From hot, heat travels from something that is hot to cold. So if the water pipe, the water here is cold, let's say it happens to be at minus 4 degrees Celsius, what will happen is the temperature on the outside of the room temperature will travel into the water pipes, and it will heat all the water throughout the house at about room temperature. Can't go higher than that. So let's say the temperature of all the water, stagnant water just resting in the pipes, is at about room temperature, or 64 degrees Fahrenheit. Now let's turn the water on. And you'll notice what happened here. When we started turning the water on, the temperature started to rise. So the temperature in these pipes right here is not exactly 64. It has various temperatures. So in the first few seconds, when I turn the water on, and I turn the water on, here it is, it's on, it's flowing here, this is the kitchen sink. The temperature of the water that is already in the pipes is what's coming through. And that started at 64, you can see it here. Started at 64, it rose a little bit to 68. And this is typical in my house, whenever I turn on the water pipes, wherever it is, whether it's this one, or that one. It starts warm, and that's because the temperature of the water within these pipes is about room temperature. So it starts warm, as it empties out, it stays warm and it seems to rise a little bit. But as it empties out, then the colder water starts to come in. And what happens here is the colder water temperature from outside is now entering the water tank, or the tankless water heater, I should say. And that cold, it hasn't had a chance to rise in temperature yet. So it's flowing now into the pipes. So the cold water from here is now flowing into the pipes. And it's being slightly heated by the warm air, the warm pipes, and the air temperature within the house. So it's slightly being heated as it travels up here. And the same thing would happen if I were to turn on this main bathroom here, and the same thing would happen here in the upper level for the bathroom in the second floor. So the cold water enters and the cold water comes in here. The warm water from the pipes has now emptied out, and the cold water is now coming through. And that's what's happening here. Okay, here's the water that's in the pipes already. Now the cooler water is starting to flow. It hasn't had a chance to heat up. Eventually the tankless water heater kicks in. All the water in here, and it's sort of a coil, is now warming up. And as it warms up, the cold water, which was originally went through, now the warm water is starting to come through, as you can see here in the graph. So this will be the outside water flowing through, and then now the warmer water coming is now entering the system. And the tankless water heater is doing its job, and up goes the temperature. Back to my little diagram. So cold water coming in. Cold water then is going to flow. But after a few seconds, the cold water starts to warm up. And now the hot water starting to flow. A little at a time, the temperature starts to rise. And eventually it will come to the maximum temperature that is being generated here. In my case, that maximum temperature is 100 degrees Fahrenheit. So 100 degrees Fahrenheit is entering here, or leaving the faucet. But I have this set but 130 degrees Fahrenheit. So why doesn't 130 degrees Fahrenheit come up here? Again, we're back to here. In simple thermodynamics, heat travels one way, from hot, I'll just fix that a little bit, hot to cold. As the hotter water starts to enter the pipes, well, the pipes are at room temperature. So heat is lost into the room. And it has to heat up the pipes, the water pipes. So it's losing heat as it heats up the water pipes, and it's also losing heat into the room as it travels through all these pipes and eventually comes here. So some temperature has been lost from here to there. Now, even though it says I've set it for 130 degrees Fahrenheit, actually I think it's 135, 130, I don't really know what the temperature is coming out there. But I do know that as hot water travels through these pipes, heat is lost. So there's going to be some heat loss. Eventually we're going to get to a maximum 100. And the same thing happens up here. Eventually it will come to about 100 degrees Fahrenheit on the second floor and here as well. So generally speaking, water comes in at about 100 degrees Fahrenheit. Sometimes it gets really warm from my experience, but typically this is it. I have a little better explanation as to what is happening here with respect to how the water flows in the pipes in a house. Let's take a look at this graph yet again. And this time I'm interested in the x-axis. In the x-axis, according to this graph, it says delta T is equal to the temperature rise, and it's in degrees Fahrenheit. In degrees Fahrenheit, get a little piece of paper here, the freezing point of water is 32 degrees Fahrenheit. So water is ice at 32 degrees Fahrenheit. Anything less than this, we're talking ice. Say 25 degrees Fahrenheit. It's less than 32, so we're talking ice. If we look at the chart, and we'll see the temperature here is 25 degrees Fahrenheit. But it's not an actual temperature. It is a temperature rise or a difference between two temperatures. Delta T represents a difference between two temperatures. So that 25 is not actually the temperature of the water. It's the difference between two temperatures. Let's have a look at that again. Delta T, keep losing my pencil. Delta T, this is the capital letter delta in the Greek alphabet. And it's often used in physics or in mathematics to represent a difference between two temperatures, or a difference between two items. Difference. Difference. I think I spelled that right. Difference between two items. So let's take temperatures. Here's a hot water tank, my tankless water heater. Water comes in and water leaves here, in and out. If the temperature going in, I'm going to use simple numbers, in degrees Fahrenheit, I'll stay in degrees Fahrenheit. If water going in is, say, 50 degrees Fahrenheit, and it gets heated, and it comes out at, for the sake of argument, 75 degrees Fahrenheit. Therefore, the change in temperature, the rise in temperature from 50 to 75 is 75 degrees minus the 25, minus the 50 I should say, is 25 degrees Fahrenheit. So the change in the two temperatures, 25 degrees Fahrenheit. That's what this represents. That 25 is a difference between two temperatures. What those temperatures are, I don't know. But that's what that represents. It's not an actual temperature. Here are the actual temperatures, temperature of water going in, temperature of water coming out. If we look further on here, let's look at 100. What that represents is, if we look at this, what that 100 means, here's my tank yet again. If water going in is 50 degrees Fahrenheit, in order to get a change in temperature of 100 degrees Fahrenheit, then the temperature of the water coming out must be 150 degrees Fahrenheit. Therefore, the change in temperature, the temperature of the water going out is 150 minus the temperature of the water coming in, because change in temperature represents the difference between two temperatures. 150 minus 50 is equal to 100 degrees Fahrenheit. That's what delta T represents. So we're looking at this chart. The rise in temperature, or the change in temperature, between the two temperatures, water going in, water going out, is represented by the x-axis. Let's take a look at delta T, or temperature rise in degrees Fahrenheit. For my little demonstration, here is the graph that I generated. And the temperature rise, well, I don't know whether I should take it from here to there. So let's do that, because this is the coldest temperature of the water coming in, that I suspect is the temperature of the water coming into the house. And eventually, the unit is going to heat up this water 200 degrees Fahrenheit. And the temperature rise is the difference between two temperatures. We'll try and keep this. So the difference between two temperatures, well, we're going to have to find two temperatures and subtract one from the other. So the maximum temperature here is 100 degrees Fahrenheit minus the lowest temperature is 58, so I'm only going to use the temperature rise for this portion. Minus 58 degrees Fahrenheit. Therefore, the temperature rise is, and I'm just sort of looking for my calculator, 100 minus 58, temperature rise of 42 degrees Fahrenheit. So the water coming in, assuming is 58 degrees Fahrenheit, and it's going to do up to 100 temperature rise, or delta T. For my kitchen sink is 42 degrees. Let's have a look at this chart one more time. I'm just going to zoom in on it a little bit. Now we have an understanding of what delta T represents. Change in temperature. It's not the actual temperatures, but a difference between two temperatures. And we have an understanding of water flow, or volume flow rate in gallons per minute. Now looking at this chart, I'm going to ignore this portion right here. Before I look at this chart, let's look up here. It has a comment. The chart below applies only to incoming water temperatures of 70 degrees Fahrenheit or less. So right now I'm in the middle of winter, or it's early February the 9th to be exact. When I did the actual experiment was a few days ago. The outside temperature is -2. Temperature of the water, I'm sure the water coming into the house is probably 45 degrees Fahrenheit. The worst scenario in order for heating water would be in the winter months. Hence the reason I waited all the way until winter in order to make this video. It says here, for incoming water temperatures greater than 70, please contact Renai. So greater than 70, I would say that would be the summer months. It's not difficult to raise 70 degrees Fahrenheit up to 100 degrees Fahrenheit. So I chose the winter in order to do this, such that the temperatures, well, it follows this, and I can use this graph. But it also requires more energy in order to raise the temperature from 45 degrees Fahrenheit up to 100. In my case, it was 58 to 100. So let's have a look at this graph. I'm going to ignore this plateau for a moment. Over here on the left, we have volume flow rate. And over here, this sloping curves, this is the change in temperature, or the temperature rise, or the amount of energy being transferred into the water from the unit. And let's look at this backwards. If we look over here at this end, we'll start at something we can relate to. Let's choose this point right here. It's 125 degrees Fahrenheit at 2 gallons per minute. So 2 gallons per minute, the heat transfer or the change in temperature is 125 degrees Fahrenheit. What that means is if water is going into the tank at, for the sake of argument, 50 degrees Fahrenheit, it will rise 125 degrees and come out at 175 degrees Fahrenheit. Here's our tank. We have in is 50, and we said the temperature rise is going to be 125. So the unit's going to heat the water up by 125. Therefore, what goes out ought to be 175 degrees Fahrenheit. So this is a low volume flow rate, 2, and it gives a high transfer rate of heat. If we start to follow this curve, and we go to the 3 mark. So at the volume flow rate of 3 gallons per minute, it intercepts this graph here at the 75, 80, 70, 80, 85 degrees Fahrenheit. So the temperature rise is 75 degrees, 85 degrees Fahrenheit at a volume flow rate of 3 gallons per minute. If we follow this curve some more to the 4 mark, 4 to about here. If we got that right, yep. And that would be 50, 55, 60. 60. So at volume flow rate of 4 gallons per minute, you notice that the temperature rise drops. So the more the volume flow rate, or the greater the amount of water flowing through the system, the greater the volume, the less the temperature rise. And that makes sense. water isn't in the system long enough in order to increase in heat, or there's too much water and it's just absorbing. It has to absorb a great deal of heat in order for it to rise in temperature. So this part of the graph sort of work at it backwards. Low volume flow rate means a high transfer of heat into the water. The greater the volume flow rate, the lower the amount of heat being transferred into the water. This part of the graph is plateaued. It's all completely flat, and frankly, I have looked at this and looked at this part, and I frankly don't quite understand why that is flat the way it is. So I'm going to have to bypass that part of the curve. This part of the curve I do understand. Over here in the far left, these are the various units that are made by Rinnai. The 199 represents 199,000 British thermal units, or BTUs. That's the amount of energy produced by that unit. 180,000 BTUs, 160,000 BTUs, and 130,000 BTUs. My unit is 160,000 BTUs, which was recommended by the contractor based on my home. Now, if you look at the numbers which we produced in this video, my volume flow rate is 1.32 gallons per minute. The temperature rise at that 1.32 gallons per minute turns out to be 42 degrees Fahrenheit. That was the temperature rise that we calculated based on my graph. If I were to plot that on this curve, 1.32 volume flow rate, temperature rise of 42 Fahrenheit, 25, 30, 35, 40, here's 45. So it ought to be about there. So the unit that I have is operating here, and this is taking temperature measurements at the faucet. Clearly, it's a far distance from what we see here on this curve, but I don't know where these temperatures were taken. It could be right at the unit, the entry and the actual exit at that point. What else does it say up here as a little note? Maximum flow rates may vary based on set temperatures, delta T and altitude. And it says here the dashed lines represent flow rate after parameter adjustments. That's these dashed lines. Again, I don't know, that I understand this. I really don't know what they did. How they managed to get a plateau here is, well, I'm unable to understand it, but I do understand this part. And it's unfortunate that my volume flow rate and temperature rise rests here. I expected it to be somewhere up here. Based on this curve, it is actually here at the point of use, at the where it exits the actual faucet. Now you have had some insight on what it's like to own a tankless water heater from, well, an actual homeowner, me. You can see the biggest drawback is, well, there isn't any hot water instantly. I have to wait 2 minutes, 1.5 to 2 minutes, before you actually get some really warm water. It's an inconvenience. I've gotten used to it. Just turn on the water. If I want to use hot water, say for washing the dishes, or if I want to take a shower, turn the water on in advance, let it run. Eventually it gets to temperature, 1.5, 2 minutes later. But when it's on temperature, it actually stays there the whole time. Question is, would I do it again? I don't know. It's an inconvenience. Maybe I should do a video on the actual cost savings, if there are any. Yeah, that's not a bad idea. Maybe I'll hold off on any decision until after I do a cost savings analysis, and I'll let you know then.